Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It's my pleasure to introduce Y.C. Tay, who joins us from the National University of Singapore. He's here in town visiting us today, and also presumably in town for Sigmetrics, which is next week. And if any of you are interested in performance analysis, and if you're not, you probably wouldn't be here, and you have not yet registered for Sigmetrics, we still have plenty of registration available. It's not too late. Love to have you at the conference. You can talk to lots of smart people, including Tay and others. He's been involved with Sigmetrics even longer than I have. And today he's going to tell us why the last 40 years of cache miss analysis should be completely thrown out and replaced with something new. So, Tay.
Thanks. So I want to thank JD for hosting the talk despite all the work that he has to do for Sigmetrics. And I appreciate your taking time to be here. Everybody is busy nowadays. To spend an hour to listen to me talk about something that actually started 10 years ago when I was in Building 26. And you can tell that it's been that long from the long list of collaborators that I have here. So how does this work? What I'm going to do is propose a research program. And here program, I use the old-fashioned sense of the word, meaning that I identify what I believe is an important problem, and then and it's a hard problem, and I propose a particular way of attacking the problem, and if that problem is solved, if the approach to attacking, if this particular way of attacking the problem works, then the problem will be solved and people wouldn't have to worry about it anymore. So it's kind of ambitious program, as all programs are. And what I'm going to do, the problem I'm going to attack is not any particular level of the memory hierarchy. I'm saying that this way of attacking the problem would work for any level of the memory hierarchy. So it's a bit audacious there. Miss equations, as JD mentioned, people have been doing this forever. What new idea do I have here? So the new idea that I have is something that I call top-down. What people have been doing in the past is what I call bottom-up. So I need to distinguish between the two of them. That's what I'm going to do first. And why is this particular way of doing it as powerful as I think it is? Because it's universal. So again, I have to explain that. And once I explain what I mean by those two, then I can explain what the research program is about. And then I'll show you some applications. So cache miss equation, everybody knows what this is. This just expresses the probability of a cache miss as a function of the cache size. So cache is everywhere in the memory hierarchy. And I don't restrict myself to any particular level. I could be talking about processor cache, or the RAM itself, or database buffer, or browser cache, etc. Size, memory is cheap, but I say that size is still a problem. You may have a humongous amount of memory, but the reality is that any particular application may be restricted to only a segment of it. So you have to worry about the memory allocation issue. Certainly you have to do that with virtualization. Or in consumer electronics, there's only a small amount of real estate, and you couldn't just say buy more memory. And then the other end of it, which Microsoft should know about, if you have a big setup with thousands of machines spinning away, data center kind of thing, then you're going to be using up a lot of all the disk that's spinning away is going to be using up a lot of energy. So size is still an issue. So although I write the cache equation as a probability of a cache miss as a function of cache size, actually is a function of two other things, the reference pattern and the management policy. And in fact, it is a very intricate interaction of these two. And that's where all the difficulty comes in. Reference pattern itself could depend on the hardware variation, whether you're talking about the data cache or the instruction cache. They have completely different reference patterns. The reference pattern could depend on the data layout, for example, how you design the index. Depends on your application mix. For example, if you have concurrency control, then that concurrency control is going to affect the timing of the reference pattern. Depends on what kind of compiler options you use, whether there's prefetching. I'm told that the biggest machines out there are actually bought by Walmart and Citibank, and for these guys, the data is changing every second, so that affects your reference pattern. And of course, the whole thing depends on how you configure it, whether you have 2 level of caches, hardware caches, 3 level hardware caches, admission control, etc. The upshot is that this whole mess is just mathematically intractable. You couldn't write enough equations to describe this system, and if you could, you couldn't solve those equations. So what do people do? They do what I call a simplified bottom-up analysis. First, you assume that it's pure LRU, that there's no prefetching, etc. Then so you get an idealized policy. And then you assume that you throw away locality and assume that the references are independent and there's only one application and there's only one process, etc. And then you get your reference pattern. Now that you have simplified everything, then you can analyze the interaction between the two of them, and you can now write an equation for the cache miss. And you compare these two pictures and you wonder, how accurate are you? So this kind of bottom-up analysis requires an expert. In any kind of performance analysis, you need to weigh what kind of approximations and what kind of assumptions you're going to make and so forth. So you need some expertise in order for the two sides to match reasonably. And if I build a model for your system, and then he says, no, I want a model too. And then, but no, my hardware is a little different, my software is a little different. Then what am I going to do? I'm going to build another one from scratch there, or am I going to somehow tweak this particular model and give it to him? Right? And if I build a model for him, and tomorrow he wants to upgrade the hardware or the software, what am I going to do? I'm going to tweak the model again. So this is just not scalable. You can't be doing this. And things get more complicated because nowadays machines are very complicated and you want it to automatically configure itself when you turn on the power, and you want it to adjust itself when the workload changes. So the whole situation is hopeless. Bottom-up analysis is not going to work going forward. So what do I propose to do? I say, let's give this up and let's do a top-down analysis instead. What do I mean by a top-down analysis? I say, let's just find one equation that will work for everything for all time. Sounds good. What would it look like? It looks something like this. Instead of just a function of the cache size, I'm going to give you a handful of parameters. All right? How does that solve the problem? Well, if I build a system for him and if you build a model for him and he wants a model, then tomorrow, then in order to port the model to him, I just have to tweak the values of the parameters. And if tomorrow he changes the hardware or the software, I just change the values of the parameters. And if you want autonomic configuration, you turn it on and the system will automatically calibrate the parameters. And if there's a workload change, then the parameters will again be calibrated on the fly. I don't have to build a new model. All the while, it's just one equation. So this is what I mean by universal. This one equation will work, it's supposed to work for all workloads, all levels of the memory hierarchy, for all time. Okay, so one equation, right? What would this equation look like? Let me write it in an alternative form, instead of probability of a cache miss, the number of cache misses. Right? You can go back and forth between these two. So the number of cache misses as a function of the cache size, m is the cache size, and 4 parameters here. And the equation looks something like this. This is my proposal of the equation. Right? May not be the right one, but I got to show you a particular example so that you see what I mean, right? So this is my proposal for the equation, and the cache size is right there. And then I have these 4 parameters. And what do those 4 parameters mean? Well, they are like the minimal ones I need. If you plot the number of misses against the memory allocation or the memory size, then of course as the memory size increases, the number of misses decreases, right? And at some point you hit the cold misses. No matter what you do, you have to page something from the disk. Okay, so these are the cold misses. Right? So n star is the number of cold misses. And then if you reduce the memory, at some point the workload just won't run anymore. Right? So there's a vertical asymptote here, which is the minimum amount of memory that you need. So that's the m naught there. Okay. Now, how is this equation different from previous equations? Well, previous equations would look like this too, except that you just keep on going down forever and ever. And that's just not true. Right? At some point, you will hit the minimum. And beyond that point, no matter how you increase the memory size, it's not going to buy you anything. So m star is this kind of like ideal memory size. If you were any smaller than this, you're going to take page faults. If you're any bigger than this, you're just wasting memory. Right? Whereas previous equations don't have this particular m star. The only parameter left is the n naught. So what's this n naught? N naught is like everything else the kitchen sink inside. Right? If you change your prefetching policy, you add prefetching or subtract prefetching, is in there. You do dynamic allocation, is in there. Basically, n naught, for example, if you do prefetching, then n naught will be a negative number. If you do dynamic allocation, then n naught is going to be a positive number. So n naught is the sum effect of all of this. Geometrically, what n naught does is control the shape of the curve. Okay, so let me illustrate this. So here we do not a single process, but multi-programming. Take Linux and 7 spec benchmarks. So these are very compute-intensive workload. You run all 7 of them together, measure the number of pages read from the disk against the RAM size. Okay, this is not a simulation, you actually measure it. And so these are the data points, and this is the, you do a fit of the equation to this. Remember, you have 4 parameters, so you can calibrate these 4 parameters. You do a kind of regression fit, and you see that it fits the data pretty well. Yeah. Real people out there don't use Linux, yeah? So let's try a Windows workload. So this one, we did Windows 2000, and here you see how old this is, right? With Business Winstone, I don't know if you guys know this, maybe this old benchmark. What they did was they actually traced some secretary or whatever using Windows 2000, cut and paste. They open up 12 applications and click on icons, etc., and then they log all of those. We replay the log, change the RAM size, measure the number of disks from the pages. And you see here, the code misses is already way up there. So this is a very I/O-intensive workload. And again, the equation does a pretty good fit. You compare the shape of the curve here and the shape of the curve previously, and you see that the shape is drastically different. And that's the n naught effect. Yeah. Okay. So I claim that the equation is universal, right? Or this particular version of the equation should be universal. So this means that if I change the replacement policy, it must still work. So this is what we did. We took Linux and then we patched it to do FIFO replacement, random replacement. So you get 3 sets of data points, and the equation fit all 3 sets of data points. Of course, you get 3 different m naught values, 3 different m star values. The code misses are the same, no matter what replacement policy you use. Right. Okay. So this is non-trivial. Getting one equation that will work for any replacement policy, this is difficult. And then I said, if I build a model for him and tomorrow he wants to change the hardware or the software, the model should still work. Okay. Okay.
Oh, I see. So the sample points are where you're fitting.
Yeah.
And so, okay, so how do you explain the variation between the sample points and your curves?
The sample point and the curves, you mean like this distance?
Yeah.
The equation is not perfect, so you can't exactly fit the center points, the data points, right?
Okay.
And part of it is also non-deterministic junk coming in, because we could not completely shut down all the processes in the machine. There are, what was this?
Okay. So, and do you have like some straw man? Equations? I mean,
sorry?
So I guess my question is, how do you know how good your equation is?
How do I know how good the equation is?
Yeah. Well, you say it's not perfect, right?
Yes.
So there would be a thing that would be perfect. And
I don't think there's any
also-
equation that can be perfect.
Okay, and then there's
Like a quadratic equation.
yeah, or
Sorry?
straw
Just
man,
anything that's
so-
fitted to those
Yeah,
data
how much
points.
worse is it than
just fitting those data points to a quadratic?
Okay, so
Yeah.
the question, so JD told me to repeat the questions in case somebody's recording this, right? Okay, so the question is, no, how do I know this is not better than the power law, let's say? So the standard way to model cache misses is to use a power equation. And we did compare with the power law. And the only way the only comparison that we did was we took the R² value. So here, it's a kind of regression, so you can measure the coefficient of determination. So the coefficient of determination for these data sets is of the order of more than 95%. Right? With the power law, you can get below 90%. So just by comparing the coefficient of determination, that's how we did it. Yeah. We cannot claim that this equation will work for everything. Right? We tried it on for certain benchmarks. The drop in the curve, the data point dropped so drastically quickly that we could not match it. And also certainly for certain syntactic benchmarks, we couldn't do it. So there are benchmarks out there that we can't. There are workloads that we can't match. Yeah.
So do you have an intuition about why that is? So in those cases, you just mentioned, what aspect of the system you're not capturing in your equation?
For some of them, so the question is when it doesn't match, why doesn't it match? For some of them, it has to do with locking or something. So, for example, at one point, we ran 2 compilations of the same file. And the data points were just all over the place, and we couldn't match it. We didn't look further into why that happened. It's just one of those things that we couldn't match, and we stayed focused on those ones that we could match. As in, it's like the Belides anomaly, right? In the Belides anomaly, even if you increase the memory size, if you run FIFO, your cache misses could go up, right? So there are always benchmarks, there are always workloads for which things work in a weird way, and we were not going to spend time on workloads that work in a weird way. We wanted to just focus on naturally occurring workloads like compilation and garbage collected applications and so forth. Certainly, if there's a real workload that doesn't match the equation and is a important workload, then we should work on it. So to answer your question, no. We don't know why sometimes it works, sometimes it doesn't work. Yeah. Okay. So as I was saying, if I build a model for him and tomorrow he wants to change the hardware or the software, then I should be able to just tweak the parameters and it should still work. So here the way to illustrate this is that we run the same Linux version and then we change the application from GCC 2.91 to 2.95. You get a different set of data points, and the equation matches the different set of of data points. And then we keep the same application, but you change the kernel. So if you remember, between 2.2 and 2.4, there was a drastic change in the Linux kernel, the memory manager. And the data points were lower, much lower than previously, and we were still able to match that. So this to illustrate that if you change the software, then it will still work.
In the Win2K model, all of the points are on one side of the line.
Yeah,
it seems like you could just tweak the parameters a little bit and push the line up, to fit those data points better.
Yeah. No, there were other points.
Oh, okay.
Yeah. This one looked really bad because it was just a simulation of Linux. Yeah. Okay. So to give you I'm claiming that this equation will work for everything, so I better give you some kind of intuition for why that might be so. So this is the equation, and let me give you the intuition for that. So to get the intuition for that, I just need to introduce three parameters, three variables. One is the average time. So assuming that this is RAM and I have pages coming into RAM, right? And every time a page comes into RAM, it stays there for a while before it gets thrown out. So let me measure the average time a page stays in RAM. So that's TRAM. And every time it gets thrown out to this, it sits there for a while before it gets called in again. So that's the average time. That will be the T disk. And R is just the number of times the pages come into RAM. Right? So if you do that, then I have something that I grandly call the references plus replacement invariant. So as I mentioned, cache misses is an interaction of the references and the replacement. You have to take care of both of them before you know what the cache miss is going to be. So what the invariant says is that this expression here is approximately equal to 1. Once you have that, and then you just have to add Little's law. This is a standard result, very robust in queuing theory, and you have the equation. Okay, so the only thing you have to worry about is, why is this invariant true? So what this invariant is actually saying is this. So remember, the pages come into RAM and they get thrown out and so forth. When it comes into RAM, it's black. When it gets thrown out into this, it's white. So when I take the average of the black parts, I get the RAM time, TRAM. If I take the average of the white parts, I get T disk. It comes into RAM 3 times, so R is equal to 3. So what the invariant is saying is that it is possible, it's likely, when you have plenty of memory around, then the R value is small. You get pitched in only a small number of times. And every time you come in, you stay there for a long time. Okay? So R is small, and this one is, so this part here is, this value is small, and this value here is large. That's one possibility. The other possibility is you are under memory pressure. If you're under memory pressure, then you get called in many times. R is large, and every time you come in, you can only stay there for a short time. Okay. That will also fit the invariant. What is unlikely is that you come in only a small number of times, and every time you come in, you get immediately thrown out. Right? This is unlikely. And it's also unlikely that you come in many times, and every time you come in, you stay for a long time. That's also unlikely. So that's basically what the invariant is saying. And as I mentioned, you add Little's law to it, and you're there. Okay. So that's where you get that. Okay. So the equation is supposed to work for everything, so that's applied to the database buffer. Here, we took data from this particular paper. These are IBM people. They measured the references on a real machine. This industrial strength kind of machine running real workloads. And then they reran the trace on different buffer pool size and measured the misses. So these are real workloads, and the equation works for these real commercial workloads. They actually have 12 traces, and we fit all but maybe one of them. Yeah. And then we tried it on a web cache. Here what we did was took a trace from one of the peer-to-peer websites in China, a lot of naughty stuff there. But from the experiment's point of view, the fit is pretty good.
So is the goal of this equation to sort of describe stuff after the fact, or to actually predict things before you change the disk or you change the memory or something like that? In other words, is the main goal of the equation to just sort of help you explain, okay, here's what my cache memory looks like, here's sort of an intuition for why that's happening? Or is it supposed to be something where, I swap out my disk for a new one, and then all of a sudden I can sort of predict what the subsequent cache memory is?
Exactly what I said.
No. At this point, you can't do that kind of a prediction, because you need the parameters, and the parameters need to be calibrated. When you dump the disk for a new disk, I don't know what the parametric values are for the new disk. So at this point, But you can do a prediction in a different sense, which I'll come to. Right? So at this point in the presentation, I'm just worried about fitting the data. Okay, so the goal is to have just one equation to fit everything. Right? But I don't think that's going to be the case. Right? So this is where the research proposal comes in. Right? I say everybody who does research in cache misses should just dump whatever they are doing and focus their expertise on just deriving one parameterized miss equation for each cache type. Okay. And do it in a top-down way. But let's postpone that point for the time being. And it seems unlikely that can actually be achieved, but I've already given you some evidence that in the case of RAM and the database buffer and the web proxy, this one equation works, actually. Why did I say that it's unlikely that one equation will work for everything? That's why you have to restrict your, scale down and say that, for each cache type, let's come up with one equation for each cache type. And the reason right off is that it doesn't seem like this will work for set associative cache. Simple reason. This particular equation is one-dimensional. There's only one m value, so it's one-dimensional. But the set associative caches are two-dimensional. Right? So it doesn't seem like the same equation might work for set associative caches. However, if you change the dimension of the set associative cache, right? To me, let's say you change from a direct map to set associative. To me, I can interpret that as changing the replacement policy. So if you change the replacement policy, the equation is supposed to still work. So it actually might still work, and it did, except that I have to change instead of I have to just add a log there. At this point, I don't know why, if I just change it to log, it works. But that's what we observed. Yeah. So let's show you some data here.
Irrespective of the set size?
We tried it for different set sizes, different line sizes.
So even like a two-way set associative and eight-way set associative, they both behave with the same. The log works.
Yeah.
That's amazing.
Yeah. With set associative caches, I think by the time you get to 8, is more or less stable.
Agreed.
Yeah.
8 should behave kind of like a fully associative cache, but I'm amazed that is similar to, say, a two-way set associative.
Yeah. It even works with one way.
That's wow.
Okay. So we did 8-way associative L2 cache. This one is a data cache. Workload, spec workload. They all use spec workloads there. So this is the data. And it has this waterfall behavior, which the equation can't cache, right? But what the equation can do is roughly match this downtrend. Right? It's not doing very well here, but for the rest of it, it's reasonable. And we tried it on instruction cache as well, and it works. So this is where the universality part of it comes in.
Yeah, again, I guess Galen already asked this, but it seems like the real question here is, okay, if I just plug those points into Excel and ask it to draw a curve through them, I'll get something that looks a lot like that. And so it seems like there needs to be some way to quantify why this is better than whatever Excel gives or GNU plot gives me if I just say fit a curve to these points.
So if I plug, if I use Excel and plug these data points, Excel will give me an equation and a fit, right? Then I will evaluate, I'll compare the two fits to see who has a better fit, right?
So, I mean,
how else can you compare?
Well, no, I agree. It's just that I guess do you have evaluations of that type that you could show us, or?
So you could do that. You could actually, fit the curve in Excel, let's say, and then fit it with your equation, and then pick some point in the parameter space that you haven't evaluated yet, right? And then see what the two curves will say, the miss rate should be.
Right.
Right, and then just see what that delta is.
Yeah. So one particular, so comparing this with what Excel might do, for example, Excel, for example, will not give you an M star value, right? Excel will come out with probably some kind of power curve. It's a polynomial or whatever, right? And if it uses a polynomial, it's going to go really bad when you scale out M, for example. It's going to go to infinity or whatever. Right? It's going to what Excel would do or what MATLAB would do is fit the particular segment of if your data is within this range, it will fit very well within this range. But when I do some kind of extrapolation, I think MATLAB and Excel will do very poorly.
Does your equation do better at that? In other words, I'll ask this. Is your equation successfully predicted at what point there's the diminishing return on memory? Because your equation has this behavior where it suddenly drops off.
Yes.
Can it predict where that point is based on, if you haven't actually collected any data past that point, can it predict where that point is?
I'll show you that.
Okay.
The prediction aspect of it. You had a question? You had a point?
Well, it's basically self-simplified.
Okay. All right. So I've explained what I mean by parameterized. I've explained what I mean by cache type. The only thing I haven't explained is this top-down modeling part of it. So what do I mean by top-down modeling? Okay, so let's look at garbage collected heap. All right. The difficulty with garbage collected applications is that if the garbage collector or whoever is responsible changes, so if you change the memory allocation, then the heap size may also change. If you have automatic automatic heap sizer somewhere in there. So if you change the heap size, then the reference pattern is going to change. Right? And this is really difficult with bottom-up analysis. In bottom-up analysis, you start off by assuming that the reference pattern is, you start off with a particular model of the reference pattern, and then you assume that this particular reference model doesn't change when you change the memory size. And that's just not so in the case of garbage collected applications. So how does the equation work for garbage collected applications like this one? So here I introduce another variable, which is the heap size. And the workload is a generational version of Mark Sweep with one of the now more or less standard decouple benchmarks, PMD. And for a heap size of 40 megabytes, these are the data points, and this is the fit. Okay. It does the fit pretty well here, not so well here. But to some extent, it's what do you want to cache. If this is what concerns you, I'm sure we can tweak the fit to do a better fit here.
Isn't that the feature, though, that differentiates your equation from just a standard?
Yeah, it is. Right. So for the purpose of this talk, I'm interested in a general fit of the rest of the curve. So for 100 megabytes, again, it's a reasonable fit. And you can complain again about this part of it, but that's not the emphasis for this particular fit that I'm demonstrating here. So notice if I change the heap size, the shape of the curve is very different, but the equation can deliver on that part of it. So it seems like the same equation works for this, except that that is the equation. The critical parameter is a heap size, so the critical variable is a heap size, and h here is nowhere in the equation. So that's not good. So what we did was we look at the parameters that we got and look at the m star value, for example, and we plotted the m star value against the heap size. And we say that we see that it's actually more or less on a straight line. So that says that the m star is actually linear in terms of h. And this already gives you some hint on heap sizing. Right? So if I give you a particular memory allocation, right, what should be the heap size? Intuitively, the bigger the heap, the better, right? Because the bigger the heap, the less garbage collection you need to do. So the bigger the heap, the better. But then you don't want the heaps to be so big that it starts going out onto disk, and then you start taking page faults. Right? Page faults are very expensive. Right? So for given memory size, memory allocation, you should just increase your heap size until the m star values equals to your memory allocation. At that point, you don't increase anymore. Because if you increase any further, then you're going to start getting page faults. So that gives you one rule about how this will help you. This gives you one rule for doing heap sizing. Then we looked at the n-naught value. The n-naught value, when plotted against the heap size, decreases and then stabilizes. Now, why would it do something like this? So remember that the n-naught is this magic with the kitchen sink inside, right? So if you do memory allocation, the n-naught value is positive. Yeah. So think about it, right? When your heap size decreases, what happens? You do more and more garbage collection. So when you do more and more garbage collection, you are allocating stuff, you're putting stuff back on the free list, you're allocating stuff, taking stuff out of the free list. So you do more and more of that, and that's why the n-naught value is going up as your heap size decreases. So that gives you another rule about this particular curve gives you another rule about heap sizing, right? You want to increase your heap size, but at some point, there's your heap is big enough to accommodate the footprint, and there's no point increasing the heap size further than that. Because if you do that, then your garbage collector is just going to walk over some idle memory. Right? So this here gives you one rule about what your maximum heap size should be. Yeah. So with these two already, you can see how you can formulate a heap sizing policy using these two parameters. But anyway, now that I've these two equations, I can plug them into that equation, and now this is my new equation for heap sizing applications now, with the heap size explicitly in the equation. And this is what I mean by top-down. Right? I start off with an equation that I know works, and then if I'm interested in some particular variable that's actually not explicitly in the equation, then I take the parameters and then I refine them. When I refine them and then put them back in, I'll have that variable explicitly in the equation. And this might not be it. You might be interested in how different variations, different garbage collectors affect the equation. So in that case, you analyze the garbage collection, how these four parameters depend on the garbage collector, and therefore refine the equation some more. Yeah. So this is what I mean by top-down. Okay, so let me zip through all the applications now. So how to power down idle memory. Yeah. So let me just use this example. So M star is here. Any memory beyond the M star is just wasting energy. You can power that down. So if you have, so here is an example. We have 3 sets of data, and you fit that 3 sets of data with the equation and use that. Once you do the fit, you have the M star value, and with the M star value now, you can power down the extra amount of memory. So by the way, that was referring to what this is an example of where you can actually do the prediction of where the M star is without any data point on this part of the curve. Yeah.
So is there a validation that that was a correct prediction?
Validation that was a correct prediction. This one is not here, but I think in the paper itself you can see how accurate or inaccurate these values are. Not in this particular slide. Okay, memory partitioning. So let's say you want to partition memory into 3 pieces. So you have 3 sets of data points. You fit them, and once you fit them, you have these 3 equations. You can take these 3. With these 3 equations, you can completely map out. So this is buffer pool 1. This is buffer pool 2. So the third one is just the difference from the total buffer pool size. And then with the equation, now you can completely map the surface. And once you know completely the surface, you can do any kind of optimization that you want. Fit any optimization criterion that you are interested in to do your optimization. TPC workload. So, as I mentioned, you want the equation to help you do dynamic adjustment of your system. So here's an example. So what we did was change the number of terminals, 50, 40, 30, etc. Simulating people coming in and going out. So the workload is dynamically changing, and we want to hold the miss rate constant at 0.2. Right? So if you ignore this part of it, you can see that the miss rates is in a cycle. Right? Now the question is whether you can fit those data points. Right? So one way to do this is gradient descent, the standard way to do it. If you do it by gradient descent without using the equation that I proposed, then what you get is something like this. Okay, which can swing violently because gradient descent is very sensitive to fluctuations. So instead of using gradient descent, what you can do is you take your data points and then you smooth out the data points. Well, how do you smooth out the data points? You use the equation to fit the data points first. After you use the equation to fit the data points, then you apply gradient descent with the equation. That will smooth out the fluctuations and release you from the tyranny of the randomness. If you do that, then the convergence is faster. But if you're going to take the data points and then fit them with the equation, then why bother doing gradient descent? You could just use the equation to predict what the memory size should be to get your 0.2. So if you do that, then you have a faster convergence. Okay. How do you use the equation? So you have this dynamic adjustment. So how do you free up memory when you have these dynamic adjustments? So here is an example with memory reclamation, and you want to do it in a fair way, right? So imagine you have a memory partition into 3 workloads, and initially one of them is unfair, right? One of the workloads, buffer pool 2, is always have a smaller miss ratio than the other 2, and the gap between the 3 of them is big. So what I want to do is I want to reduce the gap, and I don't want the same guy to win all the time. Right? So that's my idea of fairness. So
Sorry, just slightly out of scope, but why is it fair if everybody has the same miss rate? I mean, it could be that some inherently have a high miss rate, and so if you kind of push down...
This is a ratio.
So what is P star?
P star is the co-miss rate.
Sorry, that?
Co-miss rate.
Oh, okay.
Yeah. Okay. So what I want to do is free up this amount of memory. So I want to take some memory from each one of them, right? And I want to do it in a fair way. So once you have the equation, you can just do your calculus to your equation, and you see that what you get out of it is that some prorating, but the prorating is not obvious, right? You actually have to look at the M star value, the ideal allocation, and the current allocation. If you do that, then you get, after the reclamation, the gaps are smaller, and not one of them is always the winner. Database buffer tuning. Database tuning is very complicated nowadays, and all the three major vendors have put out software to help people do this. And all these three pieces of software, if you look into it, there's somewhere inside there's actually a simulator. And what the simulator does is it predicts the number of IOs for a bigger or smaller buffer. Okay? Or that's what it tries to do. Doing simulation is good. It has all the engineering details, but simulation is, means if you change the index or whatever, you have to go in and change the simulator. So it's kind of a pain. Right? That's one issue. The other issue is predicting for a smaller buffer. Now, in order to do any kind of in order to do this kind of simulation, you need to have a trace. Now, if your system is such that, or if your problem is such that you can only see the buffer, you cannot see the buffer itself is encased in a black box, and you can only see what comes out of the black box, then you can only see the misses. You cannot see the hits. And if you cannot see the hits, then when I reduce the buffer size, then the hits becomes misses, and you never saw them. So how do you actually do the simulation?
It seems like it's a little unfair to say that their problem is that they have to do simulations, because you effectively have to do a simulation too to recover what these parameters are. In other words, the equation itself doesn't have any idea, because of this n naught kitchen sink parameter. The equation doesn't give you any prediction as to what will happen, even if you make a tiny change in the software. And for example, I don't know even how sensitive you are to workload, because you showed maybe 25 slides ago, you showed that just changing the version of the kernel or changing even the version number of the compiler dramatically changes the shape of the curve. And the equation is not going to give you any visibility into how the curve will change if you make any of these tiny changes. So it seems like effectively what you're arguing for is also doing a simulation in order to recover the parameters. You're going to have to simulate either way. It's just that if you simulate the way they say, they give you the data points, but they just don't fit a curve to them. You're saying you should run a simulation to get the data points and also fit a curve to them.
Right. That's a fair criticism. That okay. So forget what I say about doing the simulation, right? Okay. So let's just go to the. There's still this other issue about what happens if you have a smaller buffer. Right. If you do a simulation with a smaller buffer, there's nothing you can do if it's within a black box. And I've been told that that situation actually arises. Maybe the one who owns the machine just doesn't want you to have access to the traces, to the reference pattern. Okay. Now, for us, there's no problem, right? If you want a smaller buffer, then I just extrapolate backwards. I don't need to know the reference pattern. Okay, so I'm on time. Yeah. So this is what I've been telling you about. Bottom-up analysis is just not scalable, and I believe that the way forward is to go for a universal equation. Do it the top-down way, a universal equation that will work for everything. And it sounds like too ambitious, but I think I've shown you some data to hopefully convince you that it's actually feasible. Yeah. And the point I want to emphasize is this. I think this is the way to do it. Give up bottom-up analysis. Yeah. Okay, so I'll be happy to answer more questions.
We had a bunch of questions during the talk. Anybody else have any other questions? Well, one that I was curious about, actually, is sort of a related work question. In the beginning, you said that the bottom-up analysis, they don't include any locality in the models. They say, that's really the case for existing?
Well, when you assume that the references are independent, you have given up locality. What's locality? Temporal locality is correlation between two references that are close in time. Spatial locality, correlation between two references close in space. These are just correlation. The minute you say independent references, you have given up your locality.
And the existing models do use independent references? Wow, that's amazingly bad.
No, there are some people who model the workload as a graph, for example. Then they keep they do keep some of the locality in that model.
But I mean, there are these simple models, like the stack distance model, where you basically say, I don't know, you assume that you kind of you have a working set, and you assume kind of how big of a stack you would. What's the distance between basically two references to the same page? And I mean, people have been using this to somehow, I mean, it's a very simple model, abstracts away a lot, but still it captures some notion of temporal locality, right?
Yeah. For that, they probably have to assume LRU, though.
Yes, that's assuming LRU.
Yeah. So you either have to simplify this or you have to simplify that. Otherwise, it's just impossible to analyze the interaction between the two of them.
I think I had a comment on your one of the last slides about database stuff. So the simulation that they do is actually it's white box simulation, it's not a black box simulation. They actually put that simulator inside of the database engine, and it sits right there in the actual cache itself. So it doesn't have the data that is cached, but it has sort of a stub, and you can see whether this is a hit or a miss. So they know about both.
Yeah. So this particular one. The SQL Server, the software, this particular resource advisor, actually,
that's totally black box.
Yeah, they use the trace to do the simulation. No, when I say black box, I mean what you suppose you are the vendor and you are doing performance analysis for some company. And the company doesn't let you look at the reference pattern. Then what do you do?
But what I'm saying is that the Oracle and DB2 stuff in here, it's actually in the database itself. So it's not like it's an external vendor that does the analysis.
Okay, then I must have misunderstood because this point was brought up to me by Narayana. So I must have misunderstood what he was saying.
These two, this is internal to the database engine. Actually,
okay, so I probably
inside of the engine.
Yeah, I should clarify that all. More questions?
Let's thank our speaker.